Suppose a 2-volt battery is connected in series with a thick filament bulb and a thin filament bulb as shown. So we're going to have plus 2 volts on the positive terminal of our battery, and we'll make the negative terminal 0 volts. And we'd like to show the distribution of surface charge along this wire. So points which are in contact with the positive terminal are going to have a lot of positive surface charge on them, compared to points which are on the negative terminal. There we'll have a lot of negative surface charge. Now, interestingly, the amount of surface charge throughout this section of the conductor doesn't change too much from the positive terminal to this point. But there is going to be a little bit of a gradient there, where there will be more surface charge toward the positive terminal than there is at this point. Surface charge will be especially pronounced around the corners here. And the same kind of thing would happen with the negatives here. All right, so at this point, we're going to have approximately 2 volts. I'm not going to say it's exactly 2 volts because there does need to be a potential difference between the positive terminal here and that point there. So why does there need to be a potential difference? Because we need to have an electric field inside the wire. It doesn't have to be a strong field, but there does need to be some kind of field which will push charge through the wire. And the surface charge is what creates the field. The same thing will happen here on the negative terminal. We'll have just a very small electric field pushing our charges through that wide section. And we'll have approximately 0 volts at this point. All right, now we can think about this like a river. And in order for the river to have continuity, then the speed of the water needs to change at certain points. Like you could think about it like a plumbing pipe, where there's a really thick section to the pipe and then a really narrow constricted section. And in this section is even more constricted. And the question is, how does the flow rate of charge through the wire compare to the flow rate of charge through the filaments? And the filaments are representing the light bulbs right now. Okay, so the flow rate of charge actually has to be the same in both. And this is always common with series circuits. The current in the thick conducting wire must equal the current in the bulbs. It's a statement of conservation of charge. So if we have an electron here, which is drifting against the field, and we have more electrons in this very thick section that are all drifting against the field, the same number of electrons that go into this narrow section have to come out. And so they're all going to pile up here, wanting to get through. In order for them all to get through, the speed has to go up. And so, just like a river, the same amount of water that flows in the thick section has to pass through the narrow section as well. So how do we get our electrons through that narrow, constricted space in a short time? What we need is a large field here. That's what causes the electrons to fly through there really quickly. Here we'll have a strong field as well, but it won't be as strong as in that very narrow section. In the thick section here, we can go back to having that very small, weak field. The principle from fluid dynamics that applies to this situation would be the cross-sectional area of one segment times the velocity of the particles in that segment has to equal the cross-sectional area in another segment times the velocity of the particles in that segment as well. This way we can have continuity. So where do the particles move slow and where do they move fast? They'll move slow in the thick sections, fast in the narrow sections, and even faster in the most narrow sections of all. So our electrons are going to need to really fly through here. Once they get to this section, they can slow back down. So the I of the wire has to equal the I of the bulbs. How do the drift speeds of the electrons compare when they're flowing in the wire versus in the bulb filaments? Well, one of the formulas we have from the past, one of them was I equals NQA times the drift speed. Let's say, just for the sake of argument, that the current and the N and the Q stay the same. When the cross-sectional area goes down, the drift speed goes up. We also have the formula E equals the resistivity times J. And J was NQVD. So if we assume that the resistivity and the N and the Q remain constant, then as our electric field goes up, the drift speed goes up proportionally as well. So as long as our bulb filaments and the conducting wire have a similar resistivity, then we expect the drift speed to go way up in the thin sections. Now, this fact has a lot of implications about what will happen in a filament when electrons are shooting through there at high speeds. The electrons will bump into other particles. They'll transfer a lot of kinetic energy. There will be a lot of vibration and a heating up of the filament substance. And there's a phenomenon called blackbody radiation in physics, where when the temperature of an object goes up, then it may emit light. And that's what happens in a light bulb filament. Now, indicate the direction and relative strength of the electric fields in the two bulbs. We had done that with the red arrows. Now we want to draw electric equipotentials inside the circuit. Alright, so here's an equipotential. This will be the 2-volt equipotential. Anywhere to the left of that is going to be a little bit less than 2 volts. That's not going to be much less, but it's a little less. Over here, we can have the 0-volt equipotential. And if we go to the right of that, we'll be at a little bit above 0 volts, but still pretty close to 0 volts. So now I have to give some numbers for the midsection here. According to the mathematics, it ends up being about 1.5 volts at this point, and approximately 1.5 volts at this point as well. Not a whole lot of potential is lost in that thick conductor. So where is there a potential difference then? It's going to be across these thin bulb filaments. And we're going to lose more potential in the very thin bulb compared to the thicker one. So let's say I put down some markings. I could mark every 0.2 volts. Alright, so we've got 0.2, 0.4, 0.6, 0.8, this is 1 volt, 1.2, and 1.4. Lots of equipotentials there because the potential is changing so rapidly and the field is so strong. Over here we can put our 1.6 and we need a 1.8 and our 2 is up there. Looks good. Alright, how does the flow rate of charge compare in the two bulbs? The eye of the thick bulb has to equal the eye of the thin bulb. A lot of times people want to say that the rate of charge is faster in the thin bulb, but that's not really the rate of charge flow. That would be the drift speed. The drift speed is fastest. So let's just make that clear. Drift speed can change in a series circuit, but current cannot. We have to have the same number of electrons leaving this part of the wire as arrive in this part of the wire. Can't leave anybody behind. We have to have conservation of charge. So if that means we have to shoot a lot of these charges through at a high speed, then that's what we'll do to get them through so that they can be with their friends. How does the potential difference across the bulbs compare? Well, the delta V of the thin filament is greater than the delta V of the thick filament. Can we compare the brightness of the two bulbs? Well, if all things are equal, if the bulbs are made out of similar materials, similar construction, then the bulb which drops the most voltage should actually be the brightest bulb because it dissipates the most power. And we can show that mathematically here in a minute. But I'm going to guess that the thin bulb is likely brighter. Now let's do the math on this to reveal how I knew that the delta V of the thick bulb would be 0.5 volts and the delta V of the thin bulb would be 1.5 volts. We want to draw our circuit using a circuit diagram. The symbol for a bulb is going to be this squiggly line, because often bulb filaments are very long and thin, and they often are coiled in this way so that you can compress a very long filament into a small space. Then we put a circle around it to make it clear that it's a bulb and not just a resistor. Alright, we've got 2 volts here. The resistance of this bulb is R1, and it's going to be given in what are called ohms. It has the letter Greek omega, and it stands for the resistance. It's a measure of the resistance of that bulb. R2 was 3 ohms. Now, like we did with capacitors, we want to do circuit simplification here. And we'll simplify our 2 circuit elements into 1. But how much resistance will it have? Well, there's a rule for series resistors. Now, any electron that leaves our negative terminal is going to have to travel through the first bulb, which is not easy to do because it's very thin, right? And then it's going to have to travel through that second bulb as well. That's not easy either. Okay, so the rule for series resistors is to add them together. It's the opposite with capacitors. When we have capacitors in series, the resulting capacitance is less than either of the 2 capacitors were alone. But when it comes to resistors, the equivalent resistance is going to be more than either of the 2 resistors alone. So let's add them. It's 1 ohm plus 3 ohms. Our equivalent resistance is 4 ohms. Okay, what I would want to do now is find the current. For that, I'm going to use Ohm's law. I equals delta V over R. So it's 2 volts over 4 ohms. It's 0.5 amps. Now the current that we had in our simplified circuit will be the same, as the current in our original circuit. It's going to be 0.5 amps in the thick wire. It's going to be 0.5 amps in the bulb, 0.5 amps in the middle part, 0.5 amps everywhere. And we can use that now, just like we did with capacitors, and we'll focus in on one circuit element at a time, and we're going to use Ohm's law on just that element now. So find delta V1 by plugging in delta V1 equals I1 times R1. Okay. And if you do that, multiply the current times the resistance, you get 0.5 volts. Now we'll do it on our second bulb. Delta V2 equals I2 times R2. It's 1.5 volts. So that's how I knew that we would drop 0.5 volts in the first bulb and 1.5 volts in the second bulb. So delta V1 was 0.5 volts. Now I want to find the power dissipated in bulb 1. To do that, we need a new formula. The formula is potential difference times current. And we'll do it for bulb 1, and then we can do it for bulb 2 as well, and compare them. So we dropped 0.5 volts across that bulb. The current was 0.5 amps. The power, therefore, will be 0.25, and power has the units of watts. Recall that delta V2 was 1.5 volts. We'd like to find the power dissipated by bulb 2. Potential drop 1.5 volts, current 0.5 amps. Looks like the power dissipated by this light bulb is 0.75 watts. So if everything else is equal about these bulbs' construction, then this one is likely to be brighter. 3 times brighter. But that's a big if. It is possible, for example, to have resistors with resistances, but they don't glow. You know, it depends on the materials being used. But if the materials used are similar, and if these bulbs do emit a good amount of light at these power levels, then bulb 2 should be brighter.